Thank you very much. I should thank you for this invitation. This is the first conference of a series of conferences that has been initiated by the French Embassy, and I think it's lovely to have this conference within the King Faisal Hospital. It's lovely, and I appreciate your invitation and this chance to talk to you and to meet very good friends and to share with you what we do at the Imagine Institute and what we could do tomorrow if we go further into a cooperation between Saudi Arabia and France, in particular King Faisal Hospital, Alfaisal University, and the Imagine Institute and Paris Descartes University. So I am a pediatric geneticist, I'm a pediatrician, a geneticist, and I am the president of Institute Imagine, an institute that is brand new, that has been inaugurated 3 years ago, and thanks to the impulsion and the willingness of President Claude Grisely, who was the founder of this institute. The first director was Alain Fischer, and now the present director is Stan Lyonnais, and I am the president of this institute. And my challenge today is to invite you to a trip from the bench to the bedside and back to the bench. So what is the Imagine Institute? It's a brand new institute that is trying to bring together all the pieces of the puzzle in terms of genetic disease in childhood. I mean, the doctors, the patients, the scientists, and the companies. And the aim, the challenge, is to offer the children the best of today's care and invent for them the medicine and the treatment of tomorrow. So this is basically what we want to do, to offer the best of the today's care and contribute to invent the future. And for this reason, we offer medical care, and we try to do the best to translate the difficult cases from the bed to the, to the bedside. For this purpose, we have a 30 reference centers for rare genetic diseases, and those 30 reference centers welcome 40,000 patients with genetic disease a year. 40,000. This figure is high figure, but I heard this morning that you guys see a great deal of patients. I heard at least 10,000 patients a year, you said this morning. So this is enormous, and we are in the frame of the same figure in terms of number of patients. So, but the value of this institute is the quality of the clinical geneticist in all different specialties: skin disease, immune deficiency, hemoglobinopathy, bone dysplasia, deafness, blindness, whatever you. And what is very, very exciting for the patient and for the doctors is that within the same institute, behind the same roof, we have recruited the best research teams on the same topics. So it's basically a clinical genetic unit, department, and a research center. And this research center is not a French-speaking center. English is the spoken language, so don't hesitate. You can come and visit and stay. There is no barrier in terms of language. We welcome scientists from the rest of the world, and the principle of the recruitment of the teams is that we launch annual calls to recruit new teams, new research teams. And we have a total of 26 research teams recruited on a competitive basis from all the world, from America, from Germany, from the UK, from Italy, and it's our pride to be able to recruit the best scientists in the field of genetic diseases. So it's rotating, it's an international call, and of course we offer a package, because you cannot attract talents without a package of money, and we offer 300,000 euro per year for 3 years, and if they do well, they are invited to stay and get a position of professor or full-time researcher in a French institution. Also, what is attractive for the scientists from the world is that we have not only this unique series of patients with genetic disease, but we also have state-of-the-art platforms in terms of genomic, bioinformatics, cell imaging, animal health, etc. And also, what is very special to this center is that we launched the first clinical trials in the same center, behind the same roof. For instance, we have a clinical research center for new drugs, and we have also a clinical research center for gene therapy. And I shall tell you more about gene replacement therapy in a minute. And also, what is extremely important, and we discussed this morning with my colleagues, is to be able to offer those new treatments to all children worldwide. How will we be able to foot the bill, to be able to pay for those new treatments if it's so expensive? And for this reason, we have invited companies to join us. And we have Alexion on board, we have Sanofi on board, we'll have more companies on board, very interested to settle in the institute because of the quality of the scientists, the quality of the patients, and this constant exchanges between scientists and doctors. Alexion, for instance, has invented a new drug that helped the cilia to grow. And for all ciliopathies, it's a unique place to launch clinical trials because they have drugs, those guys have the drug to get the cilia grow, and this may be of an invaluable contribution to treatment of some genetic disease that you also deal with. So this is very important to have companies on board. This is part of the project. Why is it part of the project? Because this project has been implemented in the frame of a big loan. We have been allocated an endowment for 10 years. A big endowment, public endowment, and the challenge is to prove that after 10 years we are going to become self-sufficient. So we get an endowment, which is very unusual in France, where equality is the rule. It's very rare to have more than your neighbor. In that particular case, President Sarkozy has launched a big loan to allocate an endowment to the best research centers in France. And 3 research centers have been allocated this endowment for 10 years. And this will end in 2020. And in 2020, we have to be self-sufficient. So this is why it's so important to have companies on board. So behind the same roof, we have all the pieces of the puzzle. So the beauty and the difficulty is that behind the same roof, you have scientists funded by the Ministry of Research, the French NIH, with their own agenda in terms of new papers, new discovery, and behind the same roof, the clinical genetics services with the reference centers and the clinical investigation unit. So different institutions, but a common goal to fight genetic disease by the means of present medicine and the medicine of tomorrow. So this is why we have the willingness to bring together behind the same roof the partners of this project. And this is how our institute looks like. It resembles to the university that I've just visited. When I pay a visit to His Excellency, the President of the University, it's a long atrium as your university. And the patients are on the first floor. The 40,000 patients are on the first floor. They see the best possible doctors in genetics that you guys know very well. Some of them you know because you have been trained with them. Alain Fischer, Jean-Laurent Casanova, Valérie Cormier, many of the best clinical geneticists in France. So the patients and doctors are first floor, and the research team that we recruited on an international basis are in the upper floors. And the platforms are behind or in the different floors. So this is a comprehensive institute designed by Jean Nouvel, that is a famous French architect, who accepted to compete for the concours, and he won the concours because he's so good. And this is in the middle of the largest French hospital, Hôpital Necker-Enfants Malades. By the way, it's the first pediatric hospital in the world, before the British. So it's 220 years old, created by the spouse of the Ministry of Finance of the King. So this is a very old and new hospital, old and new, very old with a tradition of excellency in clinical and innovation, and brand new because we have this new tool to to play. I would like to introduce a lady that has really changed the world for geneticists. This beautiful Venetian lady is called Marka Zhanna, and we are very proud of her because she and Alain Fischer has been able to succeed in the first trial for gene therapy in genetic disease. Alain and her succeeded for SCID, and we discussed SCID this morning, and this lady succeeded for sickle cell anemia and beta-thalassemia. This lady is extremely brave, and she has the ambition, not for herself, but the ambition to pave the road for the new genetics of tomorrow. And what she has done is very simple, is that she takes the bone marrow of the patient with sickle cell anemia, she can take the bone marrow stem cell progenitor, take them to the laboratory, add the missing gene, the normal gene, to the bone marrow of the patient himself, and return the bone marrow after correction to the patient. Then you have to do a myeloablation with no immunosuppression, but you have to make space for the new bone marrow. But this is an autologous bone marrow transplantation because you return the corrected cell to the patient himself or herself. So this is the beauty of this approach. You take the bone marrow of the patient, you correct the bone marrow in the laboratory, and return the corrected bone marrow to the patient. Autologous transplantation. So this is extremely elegant, and she has succeeded with SCID, and now she succeeded with sickle cell anemia, and I know how concerned you are with thalassemia and sickle cell anemia in this country. The vector is an antiviral vector, much safer than the previous ones, because they had some trouble in the past with leukemia in previous patients 15 years ago. Now they have improved the vector, and interestingly, and this is a trick that is funny, they put a tag in the normal beta globin gene. Do you know why she decided to put a tag in the normal gene? Do you have any idea or suggestion? Why was it so important to put a tag? Any suggestion? Exactly, to follow the corrected hemoglobin. So this is how she can follow the time course of hemoglobin correction in the various patients that are shown here. And you see here that progressively, the corrected hemoglobin is appearing, and this is how it happened. You stop being transfused with transfusion, and the hemoglobin, the corrected hemoglobin, is here and reach the threshold level of 10 grams per 100 of ml. So this is the time course of gene correction in a single patient. This is the sickle cell anemia hemoglobin, HbS, and this is the corrected hemoglobin. And the total, you see, is around 12, and half is the HbS, and half is the corrected hemoglobin. And then the patient does not need any longer, doesn't need blood transfusion any longer. So most of the patients are now transfusion-free for several dozens of months. They don't need any blood transfusion any longer, so it is a complete success. But of course, you geneticists in the room, you know that this is not true for all genetic disease. This is the best of medical genetics. Hematology and immunology are at the forefront of cognitive and therapeutic in genetics. They can change bone marrow. They have long been on the forefront of science, and now they are at the forefront of treatment for genetic disease. But the rest of the patient is enormous, and we have so many cases. You have thousands, dozens of thousands of patients in Saudi Arabia. We have this big figure of patients, so not all of them can be cured by gene therapy today. Only a minority of patients can be cured by gene therapy. And the first goal for us is to provide patients with a diagnosis, a proper diagnosis. This is what we badly need. At least what is the disease gene? At least give a diagnosis to the family and to the patient. And for this, goal, probably the challenge of solving the genetic heterogeneity of disease will be soon achieved. In this hospital, you do so well. I follow your article with most interest. You contribute to expanding the spectrum of new genotypes, new phenotypes in Saudi Arabia, because you have so many cases. So you know exactly what I mean. And so I am sure that you will be able to contribute at the highest level to decipher all the genetic disease in humans. But the question is not only to decipher and to solve the genetic heterogeneity of genetic disease, it's also the question a matter of addressing the question that the family addressed to you. And this is an ethical issue that is very sensitive in Europe and in France in particular. We are very eager to prevent bad commercial practice and breach of trust. And if we don't do so, if we don't offer this service to patients, they will go to 23andMe, Google, etc. So this is why it's mandatory to fulfill the expectation, to diagnose the condition, but by addressing the medical question only, and this is an obligation of me. We are not saying that we are going to predict any condition, any disease in a given individual. We simply want to address the medical question that is addressed to us. And also, a major problem in Western Europe and in France in particular is to conduct the change while preserving our common values of frugality and solidarity. Because in France, healthcare is a public healthcare system. It's not private. We are equal. You know, this is a principle of the French constitution. We are equal. We should have an equal access to diagnosis and treatment. So the healthcare system in France is a public healthcare system. So we have strong, very strong value of frugality and solidarity. And imagining that we are going to promote a two-speed medicine in France is a nightmare for us. So what we want to do is that to do so that the progress will be shared by all the citizens, because the actual progress is not only the technical progress, but also the sharing of the progress. If the progress is the privilege of the minorities, it's not a progress. The actual progress in French mentality is not the technical achievement or gene therapy for a handful of patients. This is not the actual progress. The progress is the sharing of the progress to the whole community. And I know that you are also sensible to this, because in the law, you are committed to offer the service to all the population. So this is extremely difficult to avoid a situation where we shall face a two-speed medical genetics in our country. And this is why we are eager to offer the diagnosis, but not more than the diagnosis that is needed. So this is why we have opted for a panel-first screening of known published genes. And this is not arguable by the healthcare system. First time when we went to the ministry to ask money for this panel sequencing, the Ministry of Health told me, "Doctor, you are going to do research with my money." I say, "No, we are not going to do science with your money. We are going to offer the service of the diagnosis of known disease gene to the patient. We are not doing science with your money, and we are simply offering what is an obligation of mean, that is a diagnosis of the condition, proper diagnosis of the condition." This is why I have pushed, and we have pushed, a panel-first strategy based on the presenting symptom. My child has autism. My child has intellectual disability. My child has epilepsy, or deafness, or dwarfism. So it's a strategy that is covered by the healthcare system, that don't have to pay, and this strategy is at the charge of at the expenses of the national healthcare system. What we have done at Imagine is unique because we have been able to devise these panels in collaboration between scientists and doctors. So the scientists of the institute contribute to implement the novel disease gene consistently. And the patient has full access to the state-of-the-art platform for bioinformatics and genomics. So the access of patient to platform is a facility of imaging. The supervision are the scientists of imaging. The running cost are paid by the hospital, the technical and medical staff by the hospital, and it is charged to the healthcare system. So the patient, the sick children, and their family do not have to pay. So it's a mutual benefit of patients, parents, and doctors. But also the benefit for scientists, because the scientists are become interested in a case once the known gene has been ruled out. They don't want to embark in a research project to eventually rediscover a known gene. So it's a prerequisite to sell a given case to a research team. We have to have ruled out the known gene before we offer the case to a research team. So this is a win-win offer that is supported by the scientists and the doctors, and we have developed, as you did, exactly as you did here, largely 30 service diagnosis panel at Imagine. And this figure is only to give you a sense of the diagnosis yield. You know, the best yield of the panels is for skin disorders, 95% of diagnosis, and the worst is mental retardation. And the other are in between. And you have exactly the same figure here, exactly the same. But what is interesting for us, the geneticists in the room, is when you see a figure of 95% for skin disorders, what does it mean? What does it mean to have a 95% yield?
We've discovered most of the genes.
Exactly. As Fausen said, you have discovered, we have discovered all the disease genes. So you don't have to do exome sequencing. You simply have to run the panel with 100 genes, and that's it. And we have to focus on the treatment now, not on exome sequencing all the patient, because we know that the panel is so efficient. So this is true for a certain number of panels, but it is not true for intellectual disability. And here you see your good friend Valérie Cormier, that Fausen knows very well, is a 50%. You see, retinal dystrophies is not bad, 75%. We are about to have discovered all the genetic heterogeneity, and the worst are intellectual disability. So what is this is the pipeline, because I am extremely concerned about the service to patients. I don't want to see the science on one hand and the doctors on the other, and the poor family left apart. The principle of this institution is we share. We are sharing. We are sharing. Everything that we have is shared. Good ideas, drawback, etc. So the first thing, when the child comes in, he sees very good doctor in the reference center, and most of the time we have panel. So the patient goes through the panel, and if the diagnosis is made, then it returns to clinical trial, long-term follow-up, fair enough. Prenatal diagnosis, you name it. If the diagnosis is not made by the panel, then it is channeled to the research team, if the research team is interested. Sometimes the research team is not interested, and the diagnosis is not made. And this is why I've created a special track that is called NINI, neither hospital nor research, where I can do exome sequencing for undiagnosed cases, not interested by the research teams. So this is why we do so many panels, and you know the number of panels increase parallel to exome. And briefly, and this is the end of my last part, I want to say that that NGS is not the panacea. Believe me. Maybe in your country it's easier because you know all the genetic variability in this country. But in France we have such a huge genetic heterogeneity. We don't know the extent of the polymorphism. So when we see a case and we do NGS, even panel resequencing, we never end up with one single answer, as you do. We usually end up with a handful of possible disease genes, and then we have to decide, which is sometimes very difficult. And this is why I'm very eager to include patients in the frame of a collegial inclusion, and we restitute the result in the frame of a collegial restitution. We want to include the right patient, test the right patient for the right genes, I mean the genes that are already known to be disease-causing and published, with the right interpretation. So with the combined expertise of the physician, the clinical biologist, the researcher, and the computer lab. My sense is that the loss of interaction between doctors and experts lead to serious risk of medical errors, misdiagnosis, and spoiled resources. So in a poor country, because France is not rich, being poor is about to bankruptcy, we have to save the resources. We have to spend money carefully. So this is why we are so cautious in terms of inclusion of patients. And we start with panel first, and then we move to exome if the panel is negative. And we want to have a wise inclusion and a wise discussion at restitution. I would like to focus on the most difficult problem. You know, I don't want to bother you with easy problem. I want to share with you the difficult case. It's a major issue in my country, in your country as well. I would like to share with you what we have done with our colleague from Strasbourg on 1,500 mentally retarded children. The Strasbourg Center from Jean-Louis Mandel, that you know very well, and my center, we have joint effort. And we run all the patients, the children with intellectual disability, for a handful of genes. But there are probably more than 900 disease genes in intellectual disability. And also, it's always difficult, and I preach to the converted, you know better than I, that when you face a child with mental retardation, you have to rule out environmental cause, like alcoholism, prematurity, or valproate intoxication, whatever. So it's difficult to be sure that an intellectual disability is of genetic origin. It's very difficult because you have extra genetic causes. So we start with RH-CGH, as you do, and after that we have 900 genes theoretically to be screened. It's much too much. So we start with a bench of frequent disease gene, and what we have done with our colleague from Strasbourg is that we have compared the series. It's 1,500 patients with mental retardation tested with the same approach in the two sites. Here you have the figure of the patient, the sex ratio, the severity of the intellectual disability, mild, moderate, severe, the presence of or absence of autistic spectrum disorder, epilepsy, and the consanguinity. And the funny thing is that you see that the figures are very similar in Strasbourg and Paris. Approximately the same figure for mild, moderate, and profound mental retardation. The fraction of ID with autism is also a similar figure, and the fraction of epilepsy associated to ID is similar. So here we are facing two completely random cohorts of patients in different cities, investigated with the same approach and with the same figures, not only for clinical inclusion but also for the result. And you will see that the results are amazing, because whether you are in Necker or at Strasbourg, this is a pie chart, and you see that we reach approximately the same result in Necker and Strasbourg. With the panel approach, we reach a yield of 22 to 24% of diagnosis with roughly 250 genes. 250 genes give us a yield of approximately 1/4. And we are stuck with a number of variants of unknown significance, which does not happen to you, Fausen told me this morning, because you know better than we do the spectrum of polymorphism in your population, but we don't. We don't. And this is why behind this 1/4 of diagnosis made by the panel, we have this significant fraction of variant of unknown significance. And when we are facing this, we cannot go further. The very interesting information that I'd like to share with you today also is the enormous proportion of Denovo mutation. And this is the case in France. It will not be the case in Saudi Arabia. for obvious reasons. But in France, the burden of de novo mutation is enormous. 92% in Necker, 78% of de novo mutation in Strasbourg. So having a mentally retarded child is usually a dominant de novo event in Europe. It's a recessive condition in Saudi Arabia. So completely different. But of course, if you were the mother or father of a mentally retarded child, or the sister, you are very happy to know that it is a de novo event, because if so, you can have other children in security. So this is the first service that we can offer to the family, to let them know that it's a bad luck and you can have another child. And the sister can have a child as well. So this is very important. Also, the very interesting information is that on the basis of the 1,500 cases, we have a top 20 of disease gene. So yes, there are 900 genes that are responsible for intellectual disability, but not all are equal. Some are more frequent. And here you have a list of the top 24 genes. And this is also very important for us. And most interestingly, the scenarios are not unlimited. There are 4 scenarios: synaptic proteins, transcriptional regulator, cytoskeleton, and mRNA metabolism. I shall come back to that in a minute. So we have a small number of very frequent disease gene in mental retardation in France. Also, I like panel for many reasons. First of all, because it is paid by the healthcare system. The scientists do not have to pay for this, and for this I am grateful to the panels. But also, and I would love to know what your experience is, we can detect somatic mosaicism with panel that we overlook with exome sequencing. And believe me or not, sometimes we have run on panels patient negative for exome. And after having negative exome, we went to the panel, and the panel diagnosed negative exome because of coverage, depth, quality of capture, whatever, and also mosaicism. So mosaicism in this disease, in intellectual disability, and in other genetic diseases as well, as you know, somatic mosaicism is an issue. And the more you do, the more sequencing, the more deep the sequencing, the more you will find mosaicism. And this is very interesting and very important. Also, the panel diagnose, which is not easily diagnosed by exome sequences, that is the deletion and duplication. So panels are useful as first line because you can detect a large number of patients at the expense of the healthcare system. You can detect mosaicism, and you can detect deletion and duplication that will be overlooked by exome sequencing. So this is why I keep on thinking that panel first is a wise strategy when we are a clinical geneticist, for all those reasons. Because it is covered, because you diagnose the mosaicism, and because you can detect deletion and duplication. The proportion of variant of unknown significance is largely similar in Strasbourg and Paris, 7%. I know that you have a much lower figure here in Saudi Arabia because of your perfect knowledge of the polymorphism of this population. Interestingly, the more severe intellectual disability, the higher the chance to diagnose. The milder intellectual disability, the lower the chance to diagnose. And this is obvious on the red column. The left column here is mild intellectual disability, and the right one is the severe, profound intellectual disability. And you see that you have a much greater chance to diagnose intellectual disability when the child is mentally retarded severely or syndromic. I would like to come back to clinic, because the beauty of NGS per se is not a panacea. The beauty is come back to the patient, to stratification, to to clinical follow-up before treatment, to reanalyze a posteriori the clinical presentation of the patient after stratification by etiologies. And what is interesting to me is that we have different figures in males and females, and we also have a different figure for presence or absence of autism spectrum disorder. The rate of diagnosis in Necker is 16% in a child with ASD plus ID. It's higher in Strasbourg. Epilepsy, the chance is higher in epilepsy in Necker and lower in Strasbourg. This is not absolutely clear why, but here you see that in the two centers we don't have exactly the same clinical spectrum. And also, as you have mentioned in your human genetic paper, this NGS contribute to extend the phenotypic spectrum of genetic disease. And this holds true in our science also, because based on these approaches, we have been, as you did, we have been able to extend significantly the phenotypic spectrum of those genetic disease. Interestingly, and I think it's very interesting, when you come back to function, because at one point you have to come back to the function and then to the treatment. We have indeed 900 disease genes in intellectual disability, but you don't have 900 disease scenarios. You can break down to a small number of prevalent scenarios. Synaptic, neuronal synaptic proteins, plasticity of the synapse, signaling, on this, cell projection and axon development, and cell proliferation and mobility. So when you sort the disease gene by scenarios, like system biology could do, you end up with a small number of scenarios, and which is a good news when it comes to treatment, because you may have a very heterogeneous genetic condition, but eventually you may have answers that are common to different disease genes. So at one point, I hope that we shall be able to sort all those disease genes and to address the condition using common scenarios and common therapeutic approaches. Those are the big scenarios: proliferation, migration, growth process, and synaptogenesis. So they are not exactly the same time frame during development, but the scenarios are similar in intellectual disability and autism spectrum disorder. Then it comes to the animal models, because eventually what we want to do with this gene identification is to try to find treatment. I started with the gene therapy of Marina and Alain Fischer for immune deficiencies and sickle cell anemia. But we have this burden of patients with mental retardation and many other conditions. So probably we have to go back to animal models. And now we start, we and us, everyone, try to create animal models for those different scenarios and gene for intellectual disability. And this is one example that is dear to me, because it was a very nice approach for a gene for intellectual disability that's called TBR1. And TBR1, we know that it is a gene for autistic-like behavior, mental retardation, learning disability, etc. Well, some scientists were able to build a mouse model for this condition. They created the mouse model after gene identification. And interestingly, they discovered that the mouse model mimics exactly the clinical phenotype of the patient. So this is not only curiosity, this is not only botanic, but this is the mean to try tomorrow, to test tomorrow, new drugs for this condition. So we are not going to embark for treatment of genetic disease without having proof of concept and preclinical model for that. So coming back to mouse models, or Drosophila model, or zebrafish model, with on the basis of those disease genes, is extremely important to screen drugs. So at one point, you have to come back to mouse model, even after discovering the disease gene, mouse model or Drosophila model or yeast model, simply to screen drugs before we come back to patients with new tricks and new drugs for the future. I want to, approaching the end of my presentation, I want to tell you that experience is invaluable. And experience, both in Strasbourg and in Paris, has prompted us to rethink our strategy. Panel for intellectual disability has a low diagnostic yield. It's poor, 22, 24, compared to the 95% of skin diseases. We have a high rate of variant of non-significance. And when we upgrade the panel from 250 gene to 450 gene, it has a very low impact. We move from 22 to 24 to 25 to 26. So when you add new disease gene, you don't gain much. You don't have much more. So the impact of increasing the number of genes tested is not very impressive. And it is impressive, it is valuable in case of severe intellectual disability with syndromic and with ASD. But because of this low yield, believe me or not, we have returned to smaller panels with a lower number of disease genes so as to be able to screen a larger number of patients. So because the yield is so low, as a first line, we like panel with less numerous genes, but which allows the screening of a much bigger number of patients. Because the waiting list is 6 months now. 6 months time to come back to the family. It's too long. And with the limited means that we have, we decided to reduce the number of tested genes so as to be able to screen a larger number of patients. Now, once the panel is negative, then we move to the second step, that is diagnostic whole exome sequencing when the panel is negative, and sometimes in the first case. And this morning, I have learned from Brian this brilliant idea of flash exome in situation of emergency. And I like the name. I like this initiative is superb initiative. And you should advertise this because this is exactly what we have to do in some urgent situation. There are not many situations like that. But sometimes it's important to come back in 48 hours. This morning I learned that you have the answer in 48 hours for flash exome, but in my country it's 6 months waiting, at least 6 months. And the parents are understandably very angry about us. So we have to do our best to speed up the process. I'm not talking about flash exome for everyone, but to do better. And for that purpose, we have reduced the number of disease genes so as to increase the number of patients that is tested. And if it's negative, then we move to the panel. We have started whole genome sequencing because probably whole genome sequencing at one point will be important, not only to find mutation in non-coding, but the diagnostic yield of whole genome sequencing is better for coding sequences. You see what I mean? The output, the diagnosis yield of whole genome sequencing is better because it screens the coding sequence much better. And the disease mutations that are found by whole genome sequencing are in the coding regions. So this is important. Whole exome sequencing has a limited impact. At one point, probably, we shall have to move to whole genome sequencing. But this is still extremely expensive. I have no money for that. This is not covered by the healthcare system, and I have to fund this to be able to do better for the patients. So I'm about to conclude. What are the advantages and drawbacks of panel strategy for a clinical geneticist in a country like mine? Well, the first advantage when you talk to the ministries is the consistent with the consistency with regulation and expectation of the healthcare system. They don't want me to do research with their money. Here I come back to them and say, we are not doing research. I'm simply offering a service that is an obligation of mean. And if you don't implement this obligation of mean, you will be sued by the families. So it's an obligation of mean that you should implement. So we are consistent with the healthcare system. It is relatively flexible. It is sensitive for mosaicism and deletion duplication. It is cost effective. It's not too expensive. And it is appropriate when the spectrum of disease gene is complete, like skin disorder. Then it is appropriate. It is less obvious when not all disease genes are identified, like it's the case of intellectual disability. So my sense is that this approach, this panel approach, is transient. It's not a panacea. It is not gospel truth, but it is where we are today. I want to stop at this point because I want to spend time chatting with you. What we offer at Imagine is unique. There are very limited number of centers like this one in France. In fact, there is the Imagine and Strasbourg for intellectual disability. And in some cases, only the Imagine Institute. So we are very, very eager to do the best to disseminate all those panels. Because again, the progress is not the technical progress. The actual progress is the sharing of the benefit to the population. And this is why I am so eager to share those panels with whoever wants to share them with us. It is also good because the healthcare system is charged, not the patient. This is not private. It will never become private in a country like mine. And this is also very sensitive for a country that is based on frugality and solidarity. So this is very important to stick with the common values of France. I must say that having clinical geneticists and researchers on board is extremely valuable. And it's even ideal, especially when we have the companies with that. And I would like to end up with stating, as you did in your paper, that I am convinced that NGS is not a panacea, and it will contribute to expand the spectrum of novel genotypes and clinical skills. So we have nothing to fear from NGS. We have many benefits for the present and the future of our patients. And I look forward to collaboration with your institution, your university, and your hospital because I feel very sympathetic and very familiar with your standpoint and your point of view. And thank you very much for your attention. Question? Yes, Howden. You have a microphone?
I'll just speak loud.
Okay.
So thank you very much. That was great. I'll just limit my questions to two simple questions.
Yes.
One pertains to the last point you mentioned. I think we in the clinical genetics community are facing so much of reverse phenotyping that the way clinical genetics needs to be taught will be different, and I'm sure you're going through the same kind of thought process. The second question I have is more of a technical question. I noticed that your yield for consanguineous ID cases was 10 to 17%,
yes,
which is substantially lower than what we experience. But I guess that was just limited to panels. When you put these through exome, did you notice that they actually have a higher diagnostic yield compared to the non-consanguineous? That's been our experience.
It is the case. The figure was for the panels in Strasbourg and Paris. The yield, the ratio is higher when we do exome sequencing, for sure. For the first question, I am always surprised when I see the result of NGS, because sometimes I look at the result and I say to myself, I would never have considered this diagnosis, and I would have simply overlooked the diagnosis. So NGS, both panels and exomes, contribute to expand the phenotypic spectrum of genetic disease enormously. And sometimes, you know, to the point that I doubt of the diagnosis, because sometimes it's so far from the original description, I always wonder whether it could be a coincidental situation where we find a variation that is nothing to do with the actual disease gene. So it's always difficult, and sometimes, as you do, we have patients with two conditions, not one. And probably this happened to you also, to diagnose patients with not more than one condition. So it's always difficult to interpret and to be sure when you find an atypical phenotype compared to literature. But sometimes it's true, because when we go to functional, we confirm that the variation is disease-causing. So we started the clinical delineation of syndrome by clinical genetics, and AGS now tend to expand the spectrum of the phenotypes, which is sometimes surprising for the purist. The neuropediatrician, for instance, are sometimes very surprised. But geneticists show that the spectrum, the clinical spectrum, is much broader than one originally thought. Yes? Oh, thank you.
So in the interest of saving costs and being able to diagnose patients, do you see a future time point where the efforts that we put into sequencing and identifying new alleles are so rapid that you catch up on the rate of new mutations occurring in the community,
probably,
such that you can go back to
more
genotyping as a source of being able to diagnose at least a fraction of patients in the future?
Probably, yes. This is constantly moving, continually evolving, and this I've had to do that because of limitation of resources. We have so many, the waiting list is so long, and the yield is so low that I had to adjust to our economic possibilities. So this is why I've reduced the number of tested genes as a first line. But I fully agree with you that this will be consistently revisited. And maybe we shall come back with a completely different scenario in a couple of months from now. But, you know, what is technically possible is not economically affordable in my country. You have the technical possibilities and the economic reality. And we have major cuts in the public health budget, and I have to adjust. Yes, Mr. Dean.
Thank you for the nice lecture. What about if you want to reduce the cost and the balance, is to design balance for different ethnic groups? Because in France now you have a lot of immigrants, and we see in Saudi and other that certain common diseases that can be more common than others due to the genetic, higher possibility. Do you believe that you have to design
to adjust? You have an excellent question. Thank you. It's a very good point. I should have raised it before. You have heard the question? Yes, you heard the question. The question is, owing to the immigration rate in France, will you have to adjust to special populations from Algeria, Morocco, Tunisia, whatever? Probably yes. You know why? Simply because panel sequencing for intellectual disability give a very low yield in this population. Why? Because the disease genes have been published in Western Europe and North America. This is why. And the diagnosis yield, based on the known disease gene, does not give a great deal of result in population from the Maghreb. And now we have to go to the in-depth screening of the disease gene in subpopulation. But you have to remember that this will be done on the basis of a research project and depends on the research funding to discover those genes from Kabylie or Mauritania or Western Africa, and this has to be done. Maybe at one point, this is what Frozen has raised this morning, maybe we could benefit from your experience of your genotyping here in Saudi Arabia, and to include those genes in the screening of those populations. And this is another reason to collaborate.
Ali Rodey from Kingston Mass Center.
Yes.
is a complicated always relationship between commercial entities, like companies generated by research institutions, and with the patentings and new drugs or new, let's say, Medicare advices to be in the treatment. How you are looking to this aspect in your scenarios?
We have discussed this morning also. It's a very difficult question. Many, exactly as it was said this morning, several research projects are stuck with no clinical trial, while the preclinical studies are done, animal models are convincing, reagents are there, companies are ready to embark for the trial, and we simply don't have the money to foot the bill of the clinical trials. And there are many of those cases. Even in Europe, probably joining effort is the only solution to do the clinical trials. But once the clinical trials is done, then the problem starts. Who is going to pay? Unless the price breaks down enormously, it is still extremely expensive. This morning, somebody in our meeting mentioned the figure of 800,000.
For RP65 gene therapy.
Yes, that's what thousands say. 800,000 for one patient.
For one patient.
Who can afford that? Facing a country like yours with thousands of patients waiting for a treatment. So I think that we shall probably reach a point where we could make the proof of concept in vivo, in patient. When it comes to treatment of sickle cell anemia, for instance, we shall not be able to pay that money. And this is why what Brian used to say, that premarital screening is so important. And this in your country, in our country, is such an important point. I think that we shall not be able, we're simply not able to foot that bill, neither in your country nor in mine. Too expensive. Unless the price drops down enormously, but I don't think that's going to happen. So it will be an extremely painful situation of a two-speed medicine, the medicine for the rich and the medicine for the poor. And the poor have no chance, and the rich has a chance to be cured. This is not our values. This is not our values, and this is why we are so uncomfortable. Yes, sir.
My question about the panel. I think I'm glad to hear that you start always with panel.
Yes, for the reason that I have said.
There is now a lot of demand about using panels. I would like to ask you, what's your now running time for panels? Do you set times for that, for results?
It depends on the turnover and the waiting list. It can be, depends. It can be, the waiting list for intellectual disability is awful because there are so many. But the other panel turnaround is probably 3 weeks. 3 weeks approximately. It's not the flash exome. I envy you. I envy you.
Thank you.
3 weeks to 1 month is the mean waiting time. Yes, madam.
I'd like to ask you about the price of panels. So correct me if I am wrong. You charge 2,000 euros per panel?
Yes.
So,
with including salaries, everything. It's consolidated. Guillaume has made this estimation when he was the head of the Imaging Institute, administrative head of the institute. He made this figure with some specialist, and probably it's going down, but it's the price it cost us in terms of, including salaries and taxes, all included. Reagents are not that money, but if you include the time of the biologist, the time of the technician, the time of the bioinformatic person, what it costs to the institute is 2,000.
so how much is exome?
Probably roughly the same. Roughly the same. But you have to do it in trio, for example, you see. So it threefold that money. Usually we do solo for panels. When you do exomes, you have to pay 3 times that money. And sometimes the exomes are negative, and we have to go back to panel after that. And exome, remember, is not covered by the healthcare system. Only the panel resequencing is covered. And this is...
The country is paying 2,000 per panel, yes?
Yes.
2,000 euros per panel.
Yes. Yes. But this is what it costs, including salaries, etc.
Yeah, I understand.
Which salaries are the most expensive, you know. No other questions or comment? Yes, yes, please.
Regarding the ID,
Yes.
is there any also direction for the learning disability rather than mental retardation? Because we see a lot of those recently with the new, let's say, battery, and find out these children, which usually they don't go to the medical centers because they look normal, they behave normal.
Special
schools,
schooling, yes, yes.
These things become up. Is there any studies like this in the field?
Thank you. Again, thank you for this excellent question. My ambition, my challenge is to say to the parents that the diagnosis is not the end of the story. It's the beginning of the next chapter. Because you give the diagnosis, the families, it's a relief for a family to have a diagnosis. But what I tell them in consultation is that at the end of the chapter and the beginning of another chapter, we shall do better for you, for your progeny or relative, and for special schooling as well, and one day for treatment. And what is extremely interesting, and in the future I would love to investigate this with you, is to investigate those patients after stratification by etiologies. You see what I mean? If you study all the patients together, it will, the background noise is so high that you will draw no conclusion. Now, if you investigate using neuropsychological tools, those children, after stratification by etiologies, then it's extremely interesting because there are some common features that pop out. And we have on board pedopsychiatrists and neuropsychologists that offer cognitive remediation programs. Are you aware of that? Cognitive remediation programs are those programs for intellectually disabled children using computers. And you can circumvent the problem of the child by special program and special schooling. So not only the diagnosis is important for the genetic counseling in future, but it's very important also for special schooling. Provided that you have properly characterized the child with very good experts. And this, we geneticists, we are unable to do that. We need pedopsychiatrists, neuropsychologists, and large-scale studies to delineate the spectrum, the neuropsychological spectrum and time course of those entities and offer programs. For instance, there are several situations where believe me or not, probably you will not believe me. In some cases, like ARID 1B, ARID 1B, you know this gene. The child are mentally retarded. But what popped out from this study is that they have major neurovisual problems. And if you tackle the neurovisual problem, you can circumvent part of the difficulties of the child. So when you see an mentally retarded child, you never know what is the part of visual impairment or neurosensorial impairment or visual spatial problems. Now, if you stratify the case by etiologies and investigate the children properly, then you see that the intellectual disability means nothing. And you have to investigate them in depth so as to address them properly with special schooling and cognitive remediation programs. And this is what I say to the parents, because I don't shake their hand and say bye-bye. I say, shake their hand and say, see you in 6 months from now. And they are so happy. They end up with a diagnosis and something to do. Not the drug, not immediately the drug, but something to do. They are so happy. They have something to do for the child. And this is how I conceive medical genetics. this is not the end, it's the beginning of a new chapter. Thank you very much for your attention.
Thank you very much, Professor Arnold. It was a wonderful talk, and I know you have a short visit to Saudi Arabia, but again, as you said,
I look forward next visit.
Not the end, it's
The beginning.
where I'm sure the members who are from Alfaisal Specialist Hospital Research Center and the Islamic Department and Alfaisal University would be happy to collaborate. Thanks to the French Embassy and the Cultural Attaché for their efforts toward this. And hope to see you soon again.
I look forward.
With some research
Project
plans, projects, collaborations for the sake of a better life for our future generation when it comes to genetic disease. There's small snacks outside, and we kept you until 5:30.
Thank you, Mr. Dean. Thank you very much. Thank you. Thank you very much. Thank you. Bye-bye.